Good morning, everyone. Again, welcome to our talk, Slim Device Software. We work at Access Communications. We are actually owned by Canon. My name is Umut Tezduyar Linskog.
And I'm Fredrik.
We are both software architects at Access Communications. So, at a glance, Access, our mission statement is innovating for a smarter and safer world. Our headquarters are in Lund, Sweden, pretty close to Copenhagen. We get a couple of other sites spread in Sweden for the main R&D sites, and we are around 5,000 people spread, throughout the entire world, and 62 sales offices. So we have hardware, software, and service offerings for all of these industries. And the public transport, it didn't take me too long to find one of our products on our way from the airport to here. And yeah, sure enough, your code is running inside that camera. So we are actually familiar with this stage. We came here 10 years ago and presented our journey with systemd, how we migrated to systemd. And when we had started our work or thoughts that those big distros, they weren't even really considering or debating about systemd. And as part of this migration work, we reduced our boot times to 15 seconds, which were around a minute or more than a minute range due to the extensive parallelization. And not only that, we increased our resilience. And we were able to apply resource control, resource grouping to our own services as well as the partner services so that we can actually prioritize among them. And a very important thing is that we became part of the community with our patches, with our discussions, and we believe we kept the embedded track aligned with the systemd goals back then. We had back then only one product type with maybe some minor exceptions, and that was a video product or camera. Fast forward to today, we have many different hardware products for very different industries. We have as a main product line the security cameras again. We have network intercoms. We have storage solutions. We have access control and sound products. And we have mobile cameras, body-worn cameras that Fredrik will be talking about. So at the core of all of these products lays an Access OS that we call is a proprietary but Linux-based operating system. We are very familiar with Linux. We love Linux. We released our first product, Linux-based first product, in 1990. And we transformed from a homegrown build system to Yocto in 2012. And as I said before, we released our first product with systemd in 2015. So 95% of the code base of the platform is actually open source. So we love open source, we contribute, we reuse them. And to give you guys a little bit scale, we have 200 plus products on our active track. And we make software release 6 times a year on these products. Just to give you guys a little bit more understanding, I picked up one of our products. It had 96 active systemd services on it. 10 years ago, this was maybe half the number. And this doesn't even include the on-demand activation and things that just start and die out. And finally, we are 900 plus engineers spread into 70 different teams, contributing into this platform to make different products. And due to this autonomous but distributed nature of the development model we have a lot of different set of problems.
Yeah, so 7 years ago, I was part of starting up a new product area at Access. We started doing body-worn cameras. Those are used in prisons by police officers, public transport, security guards, even cruise ships, with a mission to de-escalate and document. So this was a pretty different use case than the existing connected network cameras. So we have to optimize the software stack for battery-powered, resource-constrained and disconnected use cases. And we also got a higher security and privacy requirements as these cameras are recording in public. So those cameras are either docked and charging the battery and offloading video, or they're out in operation recording video. 2 very different use cases. And we had to make sure that only exactly the needed services and hardware are started in each scenario. So we came up with different boot modes, and those are modeled as systemd targets. So when a body-worn camera comes from the factory, it boots up in what we call activation state. And it only has one mission there, to get activated into a system. There should be no other way to contact the camera, no network connectivity outside of exactly that. It turns up in a control unit UI where an admin can accept this new device into their system. When they have done that, it reboots. Then it boots up in docked state instead, a completely different set of services running. There you can configure the body-worn camera and you can assign it to a user. And now it's ready for use. Someone will then come and pick it up from the dock, and it will reboot again into the operation state and get ready to record video. And this time the boot time is pretty important, as someone is actually waiting to use the camera. When they're done with their shift, they come back, they dock the camera again, and it reboots. Goes back into docked state, offloads the video, system logs and stuff, and then it's ready for use again. If an admin wants to remove the camera from the system, they can do so. If all content is offloaded, then it's factory defaulted and it goes back into activation state and could then go into a different system, but then it's a clean camera again. And we'll also change the CPU voltage and frequencies, the RAM config and everything between this docked state and operation state to optimize the power performance. So this actually worked very well. The body-worn camera booted fast. We got quite a good battery operation time and stuff. But those targets still included the multi-user target. And after a while, it started to deteriorate, because after some years, more and more services were started that were not intended to start. So we had our own target files defined, but they included the multi-user target. We even had like a pan-tilt zoom service, you know, these big cameras. One of those services were starting in our body-worn camera. So why did this happen? We realized we had a lack of internal guidelines on how to start a service. As you know, there's many ways to start services in systemd. You can do it by once and wanted by. You can have service files pull in other services. You can do it by target files. You can have links in target once directories. You could be activated by dbus socket and stuff. And we didn't really guide the developers on how to do this. The multi-user target is a problem of its own. It's a catch-all, and it's the default Yocto way to enable a service to start at boot. I think this is more intended for the open-ended desktop use case, where you should be able to do anything afterwards. And I think in our case, only the upstream services should be started in the multi-user target. And there's no upstream, say, Yocto-defined standard for setting up these different boot targets. So what we did was just write target files. Of course, that works, but it's messy if you want to use the Yocto layer handling. Then you have to go in and edit in these files in the layers, and that's kind of messy. There's also no easy way of blocking activations, because the services are in the image. So if someone starts them, they're going to start. But say for this first activation state, we don't want any possible bug, someone calling a dbus API to start. Maybe they start the Apache web server or something. Yeah. So what's the path forward for us? What are we doing to try to correct this? So we started organizing our services into smaller targets, not these huge use cases, but smaller targets, loosely matching technical functions. And we may use variants of these for different use cases. And we added wants on services in those new target files. And we removed the wants and wanted by from existing service files. We only keep necessary ordering like after, before, and maybe hard dependencies like requires could still be there. And then we add product type or use case specific top level targets like we did in the body-worn case. And we pull in the necessary lower level targets. But we no longer include multi-user target in those. And of course, we still need to reconfigure default target and reboot when changing use cases. So it might look like something like this. So we have the core functions in yellow. In the middle, we have what we call the common target, where all services are common for all access products are. And then we have networking, because not all products have networking all the time. In the green, we have more like the technical functions, video, audio, I/O. And then on the outside in the blue, it's more edge services like streaming and recording, big use cases. And you can even imagine then the special use cases around this, pulling in the specific ones. So now we get a manageable set of target files which we monitor. We don't get these links from multi-user target once anymore that are really hard to monitor. We make the teams responsible for the services they pull in. And we can also boot to those specific targets. We can boot to the video target in our test environment and actually measure how long it takes and which services are activated. And we do this all the time in our CI environment, and we get dashboards for this. With this, we can make a variant if the use case is slightly apart. We can make a video 2, or maybe better naming, but something like that. And we get the low-level target encoding, all the common stuff. Umut is going to talk a bit more how we can use that. So what are still the missing pieces? We still have no good way of blocking activations, because services are there. If someone by mistake starts to activate it, it will run. We have done a hack for blocking dbus activation using the dbus settings, standard system service tiers. But we can't block sockets, UDEV, or timers. We don't either want to start unneeded sockets and timer units if the corresponding services should not be enabled. And it might be good to have Yocto variables for those wants for the target files. Then we can use the layer handling in a much better way. And we could probably add functions for building the target files in the systemd BB class. And the last thing missing is an easy way to handle boot mode specific configs in an atomic way. So when we boot up this target, we want to have this set of config for the services.
Sorry, please use this one. We have radio problems.
Okay. So after working with this concept for a while, we realized that we could use it also for some resource management. So we got this bonus. So we set up slices loosely matching these targets and put a team responsible for that slice. It doesn't need to be perfectly sliced, just keep someone responsible. And then we disable the CPU controller for those slices, so we don't change the resource allocation. And now we can measure consumption of RAM and CPU in our test environments, and we can react on unexpected changes. And we intend to also expand these measurements into the live products, because these measurements are quite cheap. So that's for the targets. Now Umut is going to talk a bit more how we use a common target.
Is my mic working, or? Yeah. Okay, so one of the byproducts of what we have been trying to accomplish is a runtime modular software stack. And we would like to use this runtime modular software stack to build products that we can't even imagine today. And, but we asked the question to ourselves, like, what would be the next product that we want to build? And the answer is a virtual product. A virtual product that we can use for R&D for our own testing purposes, or a virtual product that we can use to launch in a multi-instance environment, or a product that we can just set resource groups and see how the our software is behaving. And I mean, just like any other hardware company, we are familiar with virtualization, and together we have many years of experience at Axis, and most of our virtualization attempts have been on the higher level, at the API level, in terms of mocking, which serves the purpose at that time, but over time it deviates from the original implementation and becomes just a separate product if it's not maintained. And on the other side of the scale, when we build our own system on chip, we use a QEMU to actually simulate the hardware. But imagine trying to launch 1,000 instances of the entire software with QEMU. Just doesn't scale. So what we thought is that we looked into the common layer, common target. If we could make that layer run independent of the Axis hardware, that means we can actually spread the work to the different teams, and they can go on their own pace to virtualize their part and with the measurements. So we modify the CI/CD pipeline to generate a GPT image. The same code that goes into an Axis OS product is being compiled and created, packaged as a GPT image with a kernel. So if a developer wants to use a full-blown kernel-based startup, they can use a virtual machine. But if it is too heavy that they wanted to use a container environment, that's also part of the GPT image. And when it comes to the container technology, our pick is systemd. A couple of reasons. A, it is a lot much lightweight. And B, we are a systemd system. We get all these bells and whistles with the integration. So imagine a use case that we would like to test our streaming API, 1,000 of them, so that we see how the cloud is functioning, how the user interface is functioning. I mean, it's not that we don't have 1,000 devices. We have a lot more in our test labs, but coordinating them and preparing them for these short tests is just not scaling really. So container environment is a really good pick, but the question is that how do we actually launch these many instances of the nspawn? If we were to pick one of these higher level full OCI compliant container managers, there would have been a lot of solutions out there commercially. So first thought we had was that why don't we buy a couple of hardwares using machineCTL remote, we can just launch instances, a way for us. Another path we looked into is why don't we actually buy something or pick up these softwares and have our own solution. Investigated Nomad and Ansible, which are okay, but you still have to have the infrastructure. Next thing we looked into is Fly.io, which I think is a great tool. You can say something like Fly, launch my application 100 in Brazil, and it works. And the internals is that you give them your Docker file, they take out the root file system, put user space component services on it, put their own kernel, and run it with a Firecracker virtual machine. We didn't like this path because A, we wanted to test the same user space as we do in Axis hardware, and B, we're not in control of the kernel just in case we wanted to change it. And C, I thought personally it was too expensive. We ended up using AWS EC2 with the snapshot images. And well, essentially, it boils down to the fact that you can get a EC2 machine from AWS, and you can make modifications on it, and you can take a snapshot of it. So in our case, we picked a distro, we put our own virtual machine, we configured machineCTL to start the virtual machine, and took a snapshot of it. So essentially, for every virtual machine we wanted to start, we are also starting an EC2 instance. Maybe it's not the most efficient way, but until, as a community, we come up with something much better, this was just too easy, too cheap to accomplish. And there are hooks to pass state into these virtual machines, in our case, in terms of device identity, certificate, and keys. And with that, once we wired everything, we could use the EC2 infrastructure and API and say that launch 1,000 instances in the EU region or in US region. And just to give you guys a price example, everything fit into a T2 micro machine for us. If we were to run 1,000 instances in 1 hour, the total cost would be $11.6 bucks. And the final wording is that I believe nspawn is still not working with system extensions. Maybe Luca, you can confirm that. But if it did, it would have been a great way. So this wasn't there. We had to modify the original software to actually turn on the remote debuggability through systemd. And with that, we would like to thank you guys for your time and open for questions.
Thank you. It doesn't work, and PR's welcome.
Okay, yeah.
Any question? I have a question. So I use Yocto as well. You showed your ring diagram there. Are these, for different devices, build time choices you make? And you have different builds for each device, or is it a runtime choice?
Both. But we want to make it so that you can do it as a runtime choice, because we have devices that share the same image between different hardwares for reasons.
Okay. Any other question or comment? Yes.
You described some kind of hack to prevent other services from being able to communicate with dbus. Can you elaborate a little bit on the nature of that?
So dbus has a config that you can set where it looks up which services it should activate through the dbus activation. So we actually change where that point into a directory we have that just lists our services we want to allow. And then we have like 3 of these directories, and then for each boot mode, we just point that link somewhere else.
So you mentioned you don't have something for sockets and paths, but have you thought about using a generator and just masking the stuff you don't want?
Definitely something we thought about it.
Yeah.
We just have to make sure that we will never need that socket or...
Problem with masking, I see, is that you will do everything individually. So you don't get the atomic change. So it makes a bit messy.
Correct. Any other question? Otherwise, I have more, but I prefer the audience to ask questions. I'm very interested in the security topic. So for your images, are you using the Enverti only signature and so on? Because you say you make modifications at runtime, so that's not quite compatible. How do you do that?
Yeah, so on the real device, we have our own signatures and the secure boot, really. It's not the Enverti base, but it is some kind of a similar in-house implementation.
So is your file system writable then?
We have a root file system as well as a writable file system.
Yeah, so we do all the changes in ET set.
Any other question? 1 minute. Yes.
Do you do upgrades in the field, and was that part of your targets work?
Yeah.
Yes, we do, but for the upgrading part, we use more or less an A/B scheme, where we just load the new image side by side, and then we try to boot it. And if that doesn't work, we just start the old one again.
Oh, I thought of a question. Oh, sorry. You okay? Yeah. Is this ARM-based?
We have ARM-based products mainly.
What's the oldest kernel you use?
Was it 5.14, if I'm not mistaken?
4.19. So we broke your use case because we don't support that anymore.
Yeah, I don't think 4.19 is the latest one. I believe 5.14.
So for all the active product, we are on a new enough kernel for the latest systemd.
Because we're having discussion right now about which kernels to support, and I think you have the same problem I have. What your ARM board vendor gives you a kernel, you have to use it, right? You can't just update. Yeah. Okay. Anything else? Well, actually, no, we're out of time. So let's thank the speakers. Thank you.